In our previous session, we had discussed about the introduction to airplane performance. Let us start off with the equation of motion, static and dynamic performance in this session. So to study the performance of an aeroplane, the fundamental equations that govern its translational motion through air must first be established. Consider an aeroplane in flight. The flight path's direction of motion of the aeroplane is inclined to an angle theta with respect to its horizontal. The flight path's direction and the relative wind are along the same line. The mean chord line is at a geometric angle of attack alpha with respect to the flight path. These are the four physical forces acting on the airplane. Lift L, which is perpendicular to the flight path's direction. Drag D, which is parallel to the flight path's direction. Weight W, which acts vertically towards the center of the earth and hence is inclined at angle theta with respect to the lift direction. Thrust T, which in general is inclined at the angle alpha t with respect to the flight path's direction. The flight path shown is drawn as a straight line. This is a picture we see by focusing locally on the aeroplane itself. However, if we stand back and take a wider look of the space in which the aeroplane is traveling, the flight path is generally curved. This is true if the aeroplane is maneuvering. Even if the aeroplane is flying straight and level with respect to the ground, it is still executing a curved path with a radius of curvature equal to the absolute altitude HA. When an object moves along a curved path, the motion is called curvilinear as opposed to motion along a straight line, which is rectilinear. Now Newton's second law, which is physical statement that the force is equals to mass into acceleration, consider a curvilinear path at a point on the path set up two mutual perpendicular axes, one along the direction of the flight path and the other normal to the flight path. Applying Newton's law along the flight path gives sigma F parallel is the summation of all forces parallel to the flight path, where A is equals to dv by dt is the acceleration along the flight path and v is the instantaneous value of the airplane's flight velocity. Now applying Newton's law perpendicular to the flight path, we have sigma F perpendicular is equals to mv square by rc, where sigma F perpendicular is the summation of all the forces perpendicular to the flight path and v square by rc is the acceleration normal to the curved path with radius of curvature rc. Now with these two equations are the forces parallel to the flight path, positive to the right and negative to the left, our summation of F parallel is equals to T cos alpha T minus D minus W sin theta, and the forces perpendicular to the flight path, positive upward and negative downward, are given as summation of F perpendicular is equals to L plus T sin alpha T minus W cos theta. These two equations are the equation of motion for an aeroplane in translational flight. Note that an aeroplane can also rotate about its axis. These two equations describes the general two-dimensional translation motion of an aeroplane in accelerated flight. The performance of an aeroplane for such unaccelerated flight condition is called static performance. Let us move on to the difference between static and dynamic performance. Static performance is associated with unaccelerated flight. Calculation of maximum velocity of airplane, rate of climb, maximum altitude, range, and endurance comes under static performance. Dynamic performance is associated with the accelerated flight, where we can calculate the takeoff, landing characteristics, turning flight, and accelerated rate of climb. I hope you would have understood today's session. Let us move on to thrust required in the next session. Thank you.